Generally speaking, astronomers tend to study the biggest stuff in the universe, while particle physicists study the smallest. But over the last few years, astronomers have done more and more research on a certain prediction made by string theory, one of the most popular, unproved ideas in all of physics. And let's just say the results haven't been very encouraging so far. The hope was that this might change, though, after a new study from NASA's Chandra X-ray Observatory, which tried to find evidence for string theory using galaxy collisions. But so far, things still aren't looking promising. This new study was published last month in the Astrophysical Journal, and it has 3 key pieces. There's the string theory, there's the astronomy, and there's the family of hypothesized particles that ties them all together, a group called axion-like particles. But first, the string theory. String theory is one of the major candidates for what's called a theory of everything, a single framework that could predict the results of any experiment we could ever do. Our best theories currently split the universe into the big stuff that's governed by gravity and small stuff that's modeled by quantum mechanics. Both models are great in their own domains, but try to make them overlap and funky things can happen. For instance, if you try to study gravity on the tiniest scales, any little bit of gravity should make more gravity around it. So gravity should make more gravity, should make more gravity, until you end up with an infinitely dense point where math just doesn't work. But in string theory, that can't happen. String theory supposes that all particles are actually made of tiny vibrating strings. And to make a simplification, since those strings have a sort of length, their interactions can never create a single infinitely dense point. And that stops the chaos. Different theorists find different ways to go from this stringy foundation to a universe like ours, so there are multiple versions of string theory out there. But many of them require certain kinds of new, unobserved particles to work, including some small, super light ones. They're known as axion-like particles, or ALPs. If they exist, ALPs would be so light that they'd hardly ever bump into any other kind of matter, which would explain why we've never seen one in an experiment. But a lot of researchers still think they're out there because ALPs seem like the perfect missing piece to many puzzling aspects of the universe. They're good candidates for dark matter. They could be why the universe has more matter than antimatter, and they might even explain why time only ticks in one direction. But we still haven't seen them. The good news is human-run experiments aren't the only places to look. According to string theory, ALPs should occasionally turn into photons, or particles of light, as they travel through a magnetic field, and vice versa. And for astronomers, that's pretty convenient, because space is full of light and magnetic fields. So if you looked at light after it went through one of these fields, you could look for distortions created by ALP interference. And if you saw that, well, you'd provide the evidence physicists have been looking for. Recently, this is exactly what a team of astronomers and cosmologists tried to do using the Chandra X-ray Observatory. They weren't the first to look for ALPs this way, but their observations let them look more closely than anyone had before. They used Chandra to look at light from a galaxy called NGC 1275. It's about 230 million light years away, and it's a galaxy that eats other galaxies. Collisions like that release tons of X-rays, and we can use models to predict what those X-rays should look like in an ALP-free universe as they escape the galaxy's magnetic fields. In their study, the team compared what they saw from NGC 1275 with a range of ALP models, because remember, there's no one model. Some say ALP should interact with light a lot, and others say it should be pretty rare. And in the end, well, the light from the galaxy looked exactly like we'd expect. The team saw no evidence for ALPs in their data. This doesn't mean they aren't out there, but the fact that even a super-sensitive telescope like Chandra couldn't find them does effectively eliminate a big range of possible models. Maybe an even more advanced telescope could change things in the future, but again, this Chandra study isn't the only one of its kind. Over the last couple decades, teams of astronomers around the world have looked for evidence of ALPs in their data, and none have found anything. There are still models out there that fit everyone's observations, but the field is thinning out fast, making some scientists increasingly skeptical about ALPs and some of the string theories that predict them. So axion-like particles might still exist, but if they do, they probably look pretty different from what we first expected. And as we eliminate model after model that requires them, some physicists may start looking for a theory with a few less strings attached. Thanks for watching this episode of SciShow Space News. If you're interested in astronomy and want to learn more about the field as a whole, you might enjoy a series from one of our sister channels, Crash Course. The Crash Course Astronomy series covers everything from stars to eclipses to big questions about things like dark energy. It's hosted by the amazing Phil Plait and is just a great time. You can check it out after this.